Okay, works. Can I start? Okay, so hello everyone. My name is Uwabo. Here I'm writing the two names actually here, Uwabo-Niibo. Actually, I published this work with the previous surname Niibo, so that I just put there. But now I'm Uwabo right now. And today I would like to discuss a little bit different topics that we have already discussed in this today, which is about the majoron dark matter. And that dark matter is a well-motivated dark matter candidate. It's not very recent, actually. It's a really more like historical things, but very well-motivated and very simple dark matter model. And so that here in this work, we try to estimate the updated constraint, the future prospects of that kind of dark matter model using the recent neutrino observations and also the next generation neutrino observations as well. So let me start from the very easy textbook written things. So now, so far we know that neutrino has mass, but it's not written in the standard model, so that we try to describe the neutrino mass mechanism. And there's basically two ways to describe neutrino mass. One is Dirac neutrino mass. Of course, you may say that it would be the most natural things because that's Dirac mass would be described exactly the same way with other filaments in the standard model. However, you can also say that why you have such a small, tiny Yucca coupling in that Higgs mechanism, and such people will prefer more here Majorana neutrinos by introducing the Majorana neutrino mass term for right-handed neutrino, which is the standard model singlet. And then in the case of this seesaw mechanism, if you assume that this Majorana neutrino mass is much higher than the electroweak scale, then even if that Dirac neutrino mass term is at electroweak scale, you can still explain the neutrino tiny mass. However, another question might appear is that why you have such high energy term here, and that's kind of the motivation why we consider this Majoron model. So Majoron model explains that this Majorana mass term by considering the spontaneous global U1 lepton number symmetry breaking, because this term violates the lepton number symmetry, and which is the global U1 symmetry in the Lagrangian, so let us consider the spontaneous symmetry breaking of that. So let me briefly explain what is Majoron model. So this is essentially the Lagrangian that we have. We have standard model Lagrangian and also right-handed neutrino as standard model singlet, but you also put some complex scalar, new complex scalar, which is the standard model singlet. And those terms are essentially the potential terms of this Lagrangian. And first, let me try to see the lepton number. Among those newly introduced terms, only this term, which is a Yucca coupling between the right-hand neutrino and complex scalar, is non-trivial for the lepton number. However, if you assign the lepton number 1 to right-hand neutrinos and lepton number minus to that new complex scalar, then all terms are conserves the lepton number. And due to this potential term of this newly introduced complex scalar, below the energy scale of F described here, that complex scalar will obtain the vacuum exit value. So that now I would like to reproduce this, denote this complex scalar into two real scalars, which is the small sigma and J, which is the non-constant boson and essentially what we call Majoron. And from now on, I would actually ignore this small sigma because that sigma essentially obtains the mass, which is the energy scale of F here. And here, I would like to assume that lepton number symmetry breaking happens much higher than electroweak scale. So that's real scalar will obtain the super heavy mass and essentially decouple from the low energy physics. Anyway, I would like to also show that how it works with neutrino mass. Because of that, the spontaneous symmetry breaking, below the energy scale of F, this Yucca coupling will generate the Majorana neutrino mass. And we assume that the Dirac neutrino mass would be at electroweak scale, but because we are assuming that Majorana mass will obtain the Majorana neutrino mass will be generated at the energy scale of F, which is much higher than electroweak scale. Now we are assuming that, so that the seesaw mechanism works even if both Yucca couplings are order 1. That is how the Majoron model works. So Majoron model is essentially describing the Majorana neutrino mass by assuming the spontaneous symmetry breaking or lepton number symmetry. But so far, we are not talking about dark matter. But here I would like to talk about dark matter. So people actually consider this majoron would be somehow massive because from the idea that any global symmetry in the Lagrangian in the nature would be broken somehow at from some physics that is unknown. Like, for example, the quantum gravity community has already pointed out that there's no exact global symmetry in the Lagrangian. In that case, maybe the majoron, which is the non-constant boson, would be massive, so that we can actually consider the probability of it as a dark matter candidate. And actually, it works. So, in this work, I would like to consider this majoron dark matter in this kind of dark matter mass range. That is just an assumption. But in that case, as you can see in the previous slide, the majoron dark matter actually decay into the neutrinos, of course, because of the coupling between majoron and right-hand neutrinos, and because right-hand neutrinos are mixing to the left-hand neutrino or active neutrinos, so that it can decay. However, that decay rate, if you estimate, that decay rate is actually like given in this way, which is suppressed by the neutrino mass and also the energy scale of lepton number symmetry breaking. So that if you consider this lepton number symmetry breaking is higher than 10 to 9 GeV, then actually this decay rate is easily to be a cosmological, so that particle will easily get a cosmological lifetime so that it can be a good dark matter candidate. And also I would like to emphasize that it only decay into neutrinos at tree level, so that it's a good candidate, dark matter candidate, in the sense that it has not been tested so far with the visible signals using the photons or the charged leptons, the charged fermions. So here, the main part of this talk is see the constraint on lepton number symmetry breaking energy scale by assuming that this particle is a full 100% dark matter. And because of this dark matter decay into neutrinos, essentially we have neutrino lines generated from the dark matter in the Milky Way, and this is what I would like to show in this talk. And this is the result. Okay, so here I am showing a plot of the constraint energy scale of the lepton number symmetry breaking as a vertical axis as a function of dark matter mass. Because we don't know the dark matter mass yet, but by detect the neutrino lines, we can estimate the dark matter mass, so that this is the function of dark matter mass here. And the colored regions, all colored regions are already ruled out from the current neutrino observations. And the dashed curves here is corresponding to the future neutrino detector. So this is Junos, this is hypercommutative essentially, and this is the so-called P1. And you can easily see the several features of this plot. First, you can see the stronger constraint in the higher or like a more heavier dark matter. It is essentially because the decay rate is proportional to the dark matter. And also you can see that I'm assuming that the normal hierarchy or neutrino mass with the lightest neutrino is the massless. However, if you consider the inverse mass hierarchy, or if you consider a little bit heavier neutrino mass, then actually it will enhance your decay rate. So that this constraint is, let's say, 1 order of magnitude stronger when you consider inverse hierarchy mass ordering, that kind of things. And I would like to also point out one benchmark point. Let's say 1 GeV here, which is corresponding to the 10 to 12 GeV. So in the case that dark matter mass is 1 mGeV, then the lepton number symmetry breaking must happen at higher than 10 to 12 GeV. This is the result from the neutrino observations. And you may also wonder what happened with the visible signals. Actually, you can also think about it. So not at the tree level, but if you consider the neutrino loop, N1 is the neutrino with the mass 1, so it's a neutrino loop, essentially. Then you can actually consider charged leptons or quarks at 1 loop level. And you can also think about the decay rate of those channels, and you can estimate the constraint on the majoron model using the dark matter search. However, there is one point that I would like to emphasize. So those decay rate is not actually directly connected to the energy scale, F, but as you can see, the function of the parameter, so-called K, which is the combination of a lepton number symmetry breaking energy scale and Yuka coupling. So even if you use those channels, you cannot directly constrain on the energy scale of lepton number symmetry breaking, but rather put constraint on the combination of those parameters. You can also consider the similar things for the diphotons emission from dark matter particle by considering two loops, but it is the same situation happens. What you can put constraint is not directly on the lepton number symmetry breaking energy scale, but to the combination of the parameters of this model. So finally, I would like to show the result from the visible signals rather than neutrino observations. So here I'm showing the plot where the horizontal axis is the dark matter mass again, but vertical axis is not the energy scale of lepton number symmetry breaking anymore, but the parameter, which is just schematically I write K, but it's a combination of Yuka coupling and the energy scale of lepton number symmetry breaking. And the above region of those curves are all ruled out. And there are several curves written in the same graph, but like those are corresponding to the different channels. So like, for example, the purple curve here is corresponding to the diphoton emission, and the blue curve is corresponding to, sorry, it's quite difficult to see, I guess, but like the different colors are corresponding to the different channels, different particles emitted from the dark matter particle. But anyway, so I would like to say the constraint on this here cannot be directly compared with the neutrino observations. And only when you specify your Yuka coupling, let's say 10 to minus 4 for your Yuka coupling, then you can compare with the neutrino observations. In this case, in this parameter region, this constraint is essentially same strength with the neutrino observations. Okay, so let me finalize my talk here. So in this talk, we consider the majoron model, which explain the Majorana mass term of neutrinos as a consequence of lepton number symmetry, spontaneous symmetry breaking, spontaneous lepton number symmetry breaking. And in case that we have some the explicit breaking of that lepton number symmetry as well, due to some unknown physics, let's say, but because of its global feature, it would be. Then, like, we consider that number constant boson would be the dark matter candidate. And I showed the neutrino line constraint and the visible signal constraint respectively. And as you can see, that the visible signals would put constraint on the combination of the parameter of this model, whereas in case of neutrinos, you can directly constrain on the lepton number symmetry breaking energy scale. Thank you so much.
Questions? So, do I understand correctly? It's not gauge model, no? So you not gauge lepton number, just lepton number. Yeah.
So we are not.
Yeah. No. What about production in, say, Big Bang universe?
Yeah. Great. So here I do not specify any explicit symmetry breaking term. Once if you specify the explicit symmetry breaking term, which generates the dark matter mass, then you can discuss about the production mechanism. There's many works on that. However, the disadvantage on this kind of like discussion is that once if you specify the explicit symmetry breaking term, then that because of production mechanism would be described concretely, you can actually specify the dark matter mass as well. So for example, I actually have one example here. So if you consider this explicit symmetry breaking term, then you can actually describe all production mechanism. However, the dark matter mass would be specified as well, which we did not like. We wanted the dark matter mass ranges as wide as possible, which would be only tested by the observation. That's the reason why we didn't specify the explicit symmetry breaking. Yeah.
Perfect. Questions?
Well, in one of the first slides of your talk, you put you show the origin of this J field, no? And you have the sigma and the J.
Yes. Okay.
And then, okay, the sigma from the standard model, because but you can really forget about it, or?
Oh yeah, like in this work we are just considering the recent, like the current universe. But like if you consider the early universe, and you really deal with the production mechanism of this majoron dark matter, you need to consider this sigma. But like currently it's decays, and like it doesn't it doesn't necessarily contribute to our work. Does it make sense? I hope.
Okay.
Yep. Well, if you consider the production mechanism, of course, it will play some role, of course.
And the other question is on cosmology. Because at some point in some plot, I realized there should be some constraint from cosmology also on this majoron. So can you you didn't say anything.
That's a really naive line. I would say that, like, if you have those all plots are coming from the assumption that dark matter emits the neutrino lines in the Milky Way, so that we only consider the line signals, and what we did is just like put constraint on the neutrino lines essentially. But however, you can also very naively you have the cosmological constraint on the dark matter lifetime, which must be the 10 times longer, 10 times the universe, the cosmic age of the universe, let's say. And that is, I just like put that line for the comparison with the neutrino observations. Okay. So that is the only discussed when you specify the exclusionary breaking. So that is coming from the production mechanism. And this is what we didn't like to do, because we want. It depends on the exclusionary breaking time. So, for example, this is one of the simplest case, and I think it was what was it? Sorry, I need to check it out, but I think that some of them are freezing. Yeah. But like, it will be discussed only if you specify your exclusionary breaking time.
But what the stability you need to actually compare with the rate of the decay of the J, the majoron, with the age of the universe, right? So from there, actually, you can. So basically, how you can talk about the stability of the dark matter, you basically compare with the age of the universe lifetime. So if the decay rate is greater than the age of the universe,
that is the thing. That is this curve essentially.
The black line. Yeah.
But like the neutrino observation will much stronger constraint in the most of the energy regions, so that.
Right. Yeah. One more thing. Why you are considering only the neutrino line? Like this can also give you some photon lines in the galactic center, no?
Oh yes. So in this plot, I include all the dark matter searches they are carrying on for the neutrino diphoton emission. Yes.
Okay.
But like in the other plot, I only consider neutrino lines, the Milky Way, because the neutrino observation is how to say. If you consider the extragalactic signals, it's smeared out, so it's difficult to deal with. But in this plot, I'm not showing it explicitly, but I also include kind of like everything. I mean, I combine everything that like they're coming from the Milky Way center, or coming from the extragalactic, coming from the dwarf galaxies, so etc. Yes.
Okay. Thanks.
More questions? So if not, I propose to thank the speaker of today for the stimulating talks, and then we have time to relax and discuss and write papers.